Okay, time to start with the first lecture of week 6 of the Domain-Specific Languages of Mathematics course. And we'll look at power series and ordinary differential equations, ODEs. So here are some example ODEs. So a differential equation is something where derivatives is involved and where the function is the desired output. So the first example up here says that f of x plus f prime of x equals 1. And an initial condition, as it's usually called, is that f of 0 should be 0. So notice that this is implicitly quantified over all x. So it's not just one particular value f of x we're looking for, but the whole function f. And at every point, locally, the value of the function plus the value of the derivative the variation there should in some way cancel out so that we get constant 1. On the other hand, one of the particular values of the function is also specified. If we don't, then we will have infinitely many solutions. Okay, another example, which we'll look at later, is corresponding where we look for the function little e, where the function minus its derivative is 0. And here we set the initial condition to 1 instead. And these are both first order ordinary differential equations, meaning the derivative is just one derivative here. Here we have an equation using the second order derivative. So that's the second order differential equation. And in this example, we have some function s plus its second derivative should be 0. And then when it's second order, we need two initial conditions. So here we specify both the value of s at 0 and the first derivative at 0. Now the right-hand side here, 1, 0, 0, does not have to be as simple as just a constant. It could be any function of x. As long as we know that function, then we can try to solve the differential equations. Okay, so that's the form of it, so to say, the syntax of it. Let's move further and try to solve the first example. So the idea here is to learn, to use what we learned from last week about power series. So assume that the function we're looking for can be written as an infinite sum of coefficients times x to the power of I. So we're not very explicit here about the radius of convergence for this, but at least somewhere near 0 this should hold. Okay, if we know this, then we can compute f prime sort of in the abstract without even knowing the coefficients. We know from the rules of derivative, summing, and exponential that this will also be a sum from I equals, actually, the 0th term here is ai times x to the power of 0, so that's a constant, so that will disappear. So I will start the sum from 1 to infinity. And each term, well, a constant that just remains, so we still have ai. But when we take the derivative of x to the power of I, that means we have to multiply by I, and we have to decrease the power by 1. So x to the power of I minus 1. And here you can see it's also good we started at 1, then I minus 1 is not less than 0. Otherwise we would get x to the power of minus 1 here, which wouldn't be good. Okay, so that's one of the operations we can compute. Already just knowing the form of the equation, this form, we can compute also a similar form for the derivative. And the other, the side condition here, we can try to compute what is f at 0 given this form. Well, f at 0, that's easy because every time x is raised to a power at least 1, then 0 is going to come out. So all the a1, a2, a3, and so on, whatever they are, they will disappear. So this will just be a0. So given that we said that f of 0 should be 0 here, That means we have already found our first coefficient. So f0 of 0, f0 of 0 should be 0, so a0 is equal to 0. So that follows from our taking the derivative of this format plus knowing the side condition. Okay, so I've written the left-hand side of this equation. So the left-hand side is this whole expression. I've written the left-hand side here as two big sums with a plus in between, and that's this plus. So the first sum is the f of x, and the second sum here, underlined with blue, is f prime of x. So this is trying to make it a little more concrete. And I will try to line these up in such a way that the constant terms are lined up, the x terms are lined up, the x squared terms are lined up, and so on. So let's see then, what is the constant term of the derivative? Well, it's where x is to the power of 0, so I is equal to 1. And that is then a1 times 1, so just a1. Okay, what's the second term? Well, the second term is a2 times 2 times x to the power of 2 minus 1, which is x. So here it's actually a2 times 2 times x. And not surprising then, the pattern continues. You can see this a0 becomes a1, a1 becomes 2a2, a2 becomes, well, 3a3. Let's write it in this order as I've written it above. 3 times a3, x to the power of 3, and so on. And then I've written the right-hand side aligned in the same way. And I mentioned before we could have another function, but now we have a constant function 1. So the constant part corresponding to a0 and a1 up here is 1. And all the other coefficients are 0. So it's 0 times x, 0 times x squared, 0 times x to the power of 3, and so on. So why I've written this? Well, because I want to then take the step and say, if this left-hand side and right-hand side should be equal for all x, then they need to be, the coefficients need to be equal for all powers of x. So this means that we have an equation here, which we can write out. a0 plus a1 equals 1. And we also have an equation from this, and that's the saying a1 plus 2a2 equal to 0. And let's solve these two first and then move on. So this is not a particularly difficult equation, especially since we know that a0 is 0. So if this is 0, then a1 has to be 1. So this implies a1 is 1. Now we know a1, and then we can compute a2. And the sum of 1, which is a1, and 2 times a2 should be 0. So a2 needs to be negative 1/2. Because multiplied by 2, it should be negative 1. So this implies that a2 is minus 1/2. And we know that all the other terms down here are zeros. So it means that all of the equations are going to be the form a2 is equal to minus 3a3, or a3 is minus 4a4, and so on. So if I write that in generic form, it's going to be of the shape ai equals minus I times ai plus 1. So you see, this is the ai, this is the ai plus 1, and this is, oh, sorry, it's I plus 1. So that was a good check. Let's put it in this form instead. It's the same coefficient the 3 and the 3 need to match up, 3 and 3, but this should be one smaller. So I minus 1. Oh, let's type that one again. So ai minus 1 is equal to I minus I times ai, where I is an integer then. Well, if we invert that one, we can see that a3, for example, so if we swap it around, we know that a3 is going to be minus 1 over 3 a2. No, this is not going very well. It's good that I'm also keeping track. So it's I take too many steps at once. So a3 is definitely a2 divided by. So it's minus a2 divided by 3. And in general, I will have to divide by the next number and the next number and so on. But already, without carrying out all of this computation, I mean, we've seen now, we will get the list a0 is 0, a1 is minus, a1 is 1, a2 is minus a half, a3 is minus a half divided by 3, so it's plus 1/6, and so on. It's clear that we can compute all the terms. They would be alternating signs, they would be smaller and smaller, and we can get, if we look at it more closely, a closed form for all of these terms. But even without the closed form, we can approximate the solution. So what we've shown here is that if we start out from a boundary condition of this simple form, which gives us the first coefficients, and matching the coefficients of the terms means that we can actually deduce all of the coefficients. And even if we don't deduce all of them, we get an approximation by deducing the first few. I should mention also that there's always an exam question on this, so it's well worth testing it out a bit. Yeah, here was just the place where I've written this beforehand and slightly more cleanly, perhaps, showing the pattern also in the computation. But I want to take this one step further, because we were talking about that we can actually work with this syntactic representation of power series being lists. So now when you seen that we can talk about another semantic side with the infinite sums, I also want to talk about as infinite lists. So what is then done? Well, I say up here in the title, it's about a transform. So this transform doesn't have a very fancy name like Fourier transforms and so on, but let's call it the list transform. So the idea is that instead of working with f and f prime, which are the actual semantic functions here, let's work with as and as prime, which are lists of coefficients. Because in the previous slide as well, we actually did work only with the coefficients. And how are they related? Well, they're related by the eval function. Remember, eval function actually computes from these coefficients a function f. And notice I haven't involved x here. So the function f is eval of as, meaning the function f applied to some x is eval of as and that x, which is doesn't need to be written out. So I can work directly on these as and as prime lists. So here, the prime in as prime here is just a part of the name. So it doesn't, I mean, it's supposed to signify that the coefficients are representations of the list of representing the f prime, but it's just a name. Okay, and what happens with the equation? So if I transform this equation, I get the equation on the lists, the infinite lists. So notice now this addition works on lists of coefficients. This is the part of the ring instance that we worked out last week. So an infinite list of coefficient plus an infinite list of coefficients should equal an infinite list starting with a 1 and then just being zeros. Okay, so that's the first equation. The other equation, because now I introduced two free variables here, as and as prime, is relating those two. So actually we know that the function f, if it is coded as as, is the integral of as prime. And remember, when we defined the integral, we said we have to supply also the 0th order term, the constant term. But we computed that to be f of 0. So as we know the side condition, what f of 0 is, we can insert this as the first argument to integ. So this means that even though we have two lists of coefficients, one is actually computed from the other. Okay, so now if you also remember the definition of this integration as of syntax, that definition says take this first term and just put it in the output list as the first or 0th coefficient. Then the cons operator here, it's not type here, it's the operator which puts one element in front of and then another list. And what is the other list? Well, it's a zip with function which combines sort of as a zipper the infinite list as prime with the infinite list 1, 2, 3, 4, 5, and so on, using division as the operator. That means the first element of this is divided by 1, the second element of this is divided by 2, the third by 3, and so on. So this computation will give us the whole list as if we know the list as prime. Now we don't know the list as prime, but we do know a little bit. So first of all, we know the first value of as. So okay, the first value of as is 0 because of, well, our equation solving, or our initial condition here. So I put that in green because it comes from this green box. And then we got the right-hand side, the blue box, which I put down here. And this colon here is just saying it will continue. We're not done with this list yet. So the first element of the 0th order approximation is a 0. And there's a question, how do we solve this? So we can solve it sort of by hand, iteratively, by trying to make sure that this first equation holds for each list position. So it should hold here. So the first element of this plus the first element of this should sum up to 1. So 0 plus something should be 1. Well, clearly that something has to be 1 as well. So notice that we use the information from these two sides to compute this. Okay, now we know a little bit about the derivative. We know how it starts. We know from this as prime, which is in here, we know its first element. And notice that this definition for as will insert the first element divided by 1 in this position. So directly after the first colon of as will be this value. So I've in the slides used the red arrow for this. So let's make a little red arrow saying that this 1 will be transformed into actually 1 divided by 1. Okay, and 1 divided by 1, I can actually simplify that directly and write just 1. Okay, now we've got a little bit further. We have not only the 0th order, but also the first order term. Remember, giving eval, it means that this is the function f is 0 plus x plus, and then we don't quite know. I mean, we don't know what the next term will be in here, but we will get there. And how? Well, now we have to look at what we know about the right-hand side. And the right-hand side just has lots of zeros in this case. So let's say 0, cons, 0, cons. Okay, and then we have to look at this equation again. The addition of two lists is the addition of the individual components. So 1 plus something should be 0. So this something better be -1 then. So let's insert -1 there. So that's just to satisfy this equation's second component. Okay, and now we can use the same red arrow again. We can use, let's underline this. This is the red part. It's inserting values into the definition of AS using the definition of AS prime. And given that it is already the first element, it's always one element to the right in AS compared to where it's in AS prime. So now we're at position 2 here, so we should divide by 2. So actually we get -1/2. Well, then we can just continue, go back to where we were from the beginning. We know that this equation has to be satisfied the next position. -1/2 plus something should be 0. So this better be +1/2. And with the same operation here, dividing by 3 this time, this should then be +1/2 divided by 3. So that's plus, well, I shouldn't. Let's keep black for the actual numbers. This is actually +1/6. And so on. I mean, we can continue for as long as we like. As you can see, we will always get a new term in each step. And if we just want an approximation, we already have a 0, 1, 2, third order approximation of the solution. So the solution f of x is approximately 0 plus 1 times x minus x squared half plus x3 divided by 6, and then so on, where the coefficients 1/6, -1/2, 1, and 0 are the coefficients from this list. And the translation to f is through the eval function. Okay, this was just, I had some prepared slides to make sure that I could fit this. Yeah, here I even went one step further and saw that from the 1/6, the next step, I would get to -1/24. And you might see that it will be a positive and negative sign every second time, and it will always be divided by the factorial. So if you want a closed form for all the terms, you can actually get it. Okay, this was enough for these first examples. We'll take a little break and then continue.